Our focus today is on characteristics of an exponential function. Exponential functions utilize the function notation f of x is equal to a times b to the x minus h plus k notation. Now you're going to see a lot of similarities. We have seen an x minus h before. We've seen a plus k outside of parentheses before. We've seen an a in the front of a function before. We'll talk about these as we move through your notes. The horizontal asymptote forms on the line y equals k. So, first thing we pick up is whatever our plus k value is going to be the equation or the value of the equation y equals k. If there's no k, then that's basically the same thing as saying plus 0. The horizontal asymptote is going to be y equals 0. Now, hopefully you remember that an asymptote is a line that a function approaches but never touches. So as we're thinking about exponential functions and we have lines that come down and down, they will approach but never touch a particular value. Now, if the value of a, this number in front, is negative, it's going to create a reflection over the x-axis. So my exponential decay that we have graphed here will reflect over the x-axis. If that value is greater than 1, it's going to create a vertical stretch. In other words, every value will have its value multiplied by that scale factor. We'll look at more examples of that when we deal with transformations coming up shortly. If a is between 0 and 1, just like with scale factor, it causes things to shrink. This is going to create a vertical shrink, where, again, whatever our value is for one of our ordered pairs, it will shrink by the value of our scale factor. Now, we've got to balance our understanding of shrinking and stretching by a particular scale factor with growth or decay as expressed by the value b. Because remember, the larger the value the b, the faster something will grow. The smaller the value of b, in other words, between 0 and 1, small, the faster or slower something will decay. So, numbers greater than 1 create growth. Graph will go in this fashion. Numbers less than 1 will create decay. The graphs will go in this fashion. Now, this is where we get to see some commonality. And I told you we can put parentheses around the x minus h. And we can remember that inside is the opposite, outside is the same. And we've been making that into a cheer as we've worked through the years. And I say inside and you said opposite. And I said outside and you said same. And so as we've put that ingrained into our head, we've seen it in several different functions. So if that value is a negative h, the graph is going to shift to the right, the opposite of what it seems like it should. If it's a positive h, it will shift to the left, the opposite of what it seems like it should. If we have a plus k outside, it's going to cause our graph to shift up. If we have a minus k outside, it's going to shift down. It's going to be the same as what the operation sign seems to indicate. So let's look at an example. F of x is equal to 2x raised to the x minus 3 plus 1. We can already see that this graph is moving up 1, and it is moving the opposite of negative 3, so to the right 3. For right now, though, we're going to be graphing with tables. So let's fill in our x and y's, and we always use -2, -1, 0, 1, and 2. And out of habit, I always start with 0 as my first x value. 0 minus 3 is -3, so 2 to the -3rd power plus 1. Well, 2 to the -3rd power is the same thing as 1 over 2 to the 3rd power plus 1, which is the same thing as 2 times 2 is 4 times 2 is 8. 1 over 8 plus 8 over 8 gives me a 9 over 8. All right, let's plug in a positive 1. Well, if I put a positive 1 in there, we have 1 minus 2 is -3. So that's going to give me 1 minus 3 is -2. Give me 2 to the -2nd power plus 1, which is 1 over 2 squared, or 1/4, plus 4 over 4, gives me a 5 over 4. All right, let's go on to the next one. Plug in a 2. 2 to the -1st power plus 1. Well, 2 to the -1st power is 1 over 2 plus 2 over 2, which is 3/2. Let's graph these and see what they look like. We go over 2, we go up 3/2. That's 1.5. We go over 1, we go up 1.25. We go over nothing, we go up 1.125. We should realize, hey, we are approaching this line really fast. And it's not going to go above that line. Why is it not going above that line? Because we're adding 1 to everything. That adding 1 is the value of our horizontal asymptote. Y equals 1. Okay, well, our graph didn't really give us a good direction on what's happening as we move away from or higher in values. Now, sometimes -2, -1, 0, 1, 2 is not going to work for you. Like in this instance, I probably need something like a 4 so that I can end up with a positive power here, so that I can finally end up with a number that is much higher than just 1 and 1.5. So if we plug in a 4, we get 4 minus 3, which gives me 1. So 2 to the 1st power plus 1. 2 to the 1st power is 2, plus 1 is 3. That's finally got a little bit more momentum. We come over 4, we go up 1, 2, 3. And now we're starting to see some growth. We could do the same. I could add a 5 for my x value. And so if I put a 5 in for x, 5 minus 3 is 2. So that gives me 2 squared plus 1. 2 squared is 4 plus 1 is 5. And so we can see if I came over 5, that would bring me up 5. And we would eventually keep growing. Concavity, we're looking for where is the bowl facing. Is the bowl facing up or is the bowl facing down? In this case, the bowl is still facing up. Domain and range. Well, domain, let's think about the furthest left x value. We can plug any x value we want in and we will always get an outputted y value. So domain is -infinity. Come on. Let's do it that way. -infinity to infinity. Well, what about range? Well, we just said that at this equation, y equals 1. That's our asymptote. Our graph is approaching it, but never touching it. So really, any value above our asymptote would be part of the range. So x is greater than 1. End behavior. We want two statements here. As x approaches -infinity and as x approaches positive infinity. So as x approaches -infinity, in other words, my x's go further and further to the left. What are my y's doing? Well, they're getting closer to this asymptote. So my y is approaching 0. Sorry, not 0. Our asymptote's not at 0 for this problem. They are approaching 1. All right. As my x's are getting larger, my y's are approaching, well, they're going to go on and on forever because it's going up really fast. So my y's are approaching infinity. Intercepts. X-intercepts. Well, our x-intercepts, where does it intercept the x-axis? This particular graph will never intercept the x-axis, so we can say none. Y-intercept, where does it intercept the y-axis? Well, from the graph, I can tell it's kind of hard to tell what that value is. That's where the chart comes into play. Or you may just have to plug 0 into the function if you haven't done so already. So that gives us 0.9/8. Interval of increase or decrease. Well, is our graph going up or is it going down? In this case, it's increasing. When did it first start increasing? We know it's gradually approaching the asymptote, y equals 1. So somewhere way back here, it's really close to 1. But again, we can put any x value in, and we're going to constantly get values of y that are closer and closer and closer to 1. So it starts increasing at negative infinity. When does it stop increasing? It's going to get steeper and steeper, but it's going to go increase forever and ever. These are your typical characteristics of exponential functions.